When dealing with electrical tap conductors, proper grounding is crucial for safety. A question arises regarding the correct size of the grounding conductor for a 350 kcmil tap connected to a bus protected by an 800 amp circuit breaker, with the tap conductors terminate in a 200 amp circuit breaker less than 25 feet away. The National Electrical Code, or NEC, specifically Table 250.122, provides guidance on size and grounding conductors. The grounding conductor for the 350 kcmil tap should indeed be a minimum of 1/0, as per the 2002 NEC Table 250.122. The tap is protected by an 800 amp circuit breaker. Table 250.122 dictates the minimum size of the grounding conductor based on a rating of the overcurrent protection device, or UCT, protecting the circuit. For an 800 amp UCT, the minimum grounding conductor size is 1/0. This requirement holds true regardless of the fact that the tap conductors terminate in a 200 amp circuit breaker downstream. The crucial point to understand is that the grounding conductor size is determined by the UCT ahead of the tap, not the UCT downstream. In this specific scenario, the 800 amp circuit breaker is the UCT ahead of the tap. The argument suggesting that a number 6 grounding conductor is sufficient because the downstream circuit breaker is rated at only 200 amps is incorrect. The NEC mandates that the grounding conductor be sized according to the UCT protecting the circuit at the source, which in this case is the 800 amp circuit breaker. Understanding the principles behind grounding conductor sizing is essential for ensuring electrical safety. Firstly, the grounding conductor provides a low impedance path for fault current to return to the source. This low impedance path facilitates the rapid clearing of a fault by the overcurrent protection device. A properly sized grounding conductor ensures that the fault current is sufficient to trip the circuit breaker or blow the fuse, thereby preventing dangerous voltage on equipment enclosures and reducing the risk of electrical shock. Secondly, the grounding conductor plays a critical role in minimizing the potential difference between conductive parts of equipment and ground. By bonding all conductive parts of the electrical system to a common ground, the grounding conductor helps to equalize the voltage potential, reducing the likelihood of electric shock hazards. Thirdly, the grounding conductor helps to stabilize the voltage during normal operation. By providing a reference point for the electrical system, the grounding conductor helps to maintain a stable voltage level, preventing voltage fluctuations that can damage equipment. When sizing grounding conductors, it is essential to refer to the appropriate tables in the NEC. Table 250.122 provides the minimum size of the equipment grounding conductor for grounded systems. This table is based on the rating or setting of the overcurrent protection device in the circuit ahead of the equipment, raceway, or enclosure. It is important to note that the grounding conductor size specified in Table 250.122 is the minimum acceptable size. In some cases, it may be necessary to increase the size of the grounding conductor to meet specific requirements, such as those related to voltage drop or fault current carrying capacity. In addition to Table 250.122, the NEC also provides guidelines for sizing grounding conductors for ungrounded systems. Section 250.166 specifies the requirements for sizing the grounding electrode conductor for ungrounded alternating current systems. This section requires that the grounding electrode conductor be sized based on the size of the largest ungrounded conductor in the system. Furthermore, it is crucial to consider the material of the grounding conductor. Copper is the most commonly used material for grounding conductors due to its excellent conductivity and corrosion resistance. However, aluminum conductors are also permitted under certain conditions. When using aluminum grounding conductors, it is important to ensure that they are properly sized and installed to prevent corrosion and ensure reliable performance. In addition to sizing and material considerations, proper installation of grounding conductors is essential for ensuring electrical safety. Grounding conductors must be securely connected to equipment enclosures, raceways, and other conductive parts of the electrical system. The connections must be made using approved methods and materials to ensure a low impedance path for fault current. Furthermore, grounding conductors must be protected from physical damage and corrosion. They should be installed in a manner that minimizes the risk of mechanical stress, abrasion, and exposure to corrosive environments. Regular inspection and maintenance of grounding conductors are also important for ensuring their continued effectiveness. Grounding conductors should be visually inspected for signs of damage, corrosion, or loose connections. Any deficiencies should be corrected promptly to maintain the integrity of the grounding system. In summary, understanding the principles of grounding conductor sizing and installation is essential for ensuring electrical safety. By following the guidelines in the NEC and adhering to best practices, you can help to protect people and property from the hazards of electrical shock and fire. Remember to always consult with a qualified electrical professional for guidance on specific grounding requirements and installations. When dealing with tap conductors, the overcurrent protection device protecting the main feeder determines the size of the grounding conductor, not the overcurrent protection device protecting the tap conductors downstream. For instance, consider a scenario where a 480-volt feeder is protected by a 400-amp circuit breaker. Tap conductors are taken from this feeder to supply a machine. These tap conductors are protected by a 60-amp circuit breaker at the machine. According to the NEC, the equipment grounding conductor for the tap conductors must be sized based on the 400-amp circuit breaker protecting the main feeder, not the 60-amp circuit breaker protecting the tap conductors. Referring to NEC Table 250.122, a 400-amp overcurrent protection device requires a minimum number 3 copper equipment grounding conductor. Therefore, the tap conductors must be installed with a minimum number 3 copper equipment grounding conductor, regardless of the size of the tap conductors or the 60-amp overcurrent protection device. This requirement ensures that a fault on the tap conductors will have sufficient fault current to trip the 400-amp circuit breaker, providing adequate protection for the entire circuit. It is important to note that the NEC does allow for some exceptions to this rule. For example, if the tap conductors are no more than 10 feet long and are installed in a raceway or cable armor, the equipment grounding conductor can be sized based on the overcurrent protection device protecting the tap conductors. However, this exception is only allowed under specific conditions and should be carefully evaluated before being applied. In addition to the NEC requirements, there may be local codes or regulations that further restrict the size or type of equipment grounding conductors that can be used. It is important to consult with local authorities to ensure compliance with all applicable codes and regulations. Proper sizing and installation of equipment grounding conductors are essential for ensuring the safety of electrical systems. By following the NEC requirements and consulting with qualified electrical professionals, you can help to protect people and property from the hazards of electrical shock and fire. Furthermore, when discussing grounding conductors, it's beneficial to understand related concepts such as bonding jumpers. Bonding jumpers are used to connect metallic parts of an electrical system together, creating a low impedance path for fault current. These jumpers are critical for ensuring that all metallic parts are at the same electrical potential, reducing the risk of electric shock. Main bonding jumpers, for example, connect the equipment grounding conductor to the grounded conductor neutral at the service equipment. This bond ensures that fault current can flow back to the source, tripping the overcurrent protection device. Equipment bonding jumpers, on the other hand, connect metallic enclosures, raceways, and other non-current carrying metal parts to the equipment grounding conductor. This ensures that these parts are effectively grounded, minimizing the risk of electric shock if a fault occurs. The NEC provides specific requirements for sizing and installing bonding jumpers. The size of the bonding jumper is typically based on the size of the largest ungrounded conductor in the circuit. The jumper must be securely connected to the metallic parts using approved methods, such as listed connectors or exothermic welding. In addition to bonding jumpers, grounding electrodes play a crucial role in providing a path for fault current to ground. Grounding electrodes are typically metal rods, pipes, or plates that are buried in the earth. They provide a connection to the earth, allowing fault current to dissipate safely. The NEC specifies the types of grounding electrodes that are permitted and the requirements for their installation. Common types of grounding electrodes include ground rods, metal water pipes, and concrete encased electrodes used for grounds. The number and spacing of grounding electrodes are also specified in the NEC. In many cases, multiple grounding electrodes are required to ensure a low impedance path to ground. The installation of grounding electrodes must comply with the NEC requirements, including the depth of burial and the type of connections used. The connections must be made using approved methods and materials to ensure a reliable and corrosion-resistant connection. Regular inspection and testing of grounding electrodes are also important for ensuring their continued effectiveness. The resistance of the grounding electrode system should be measured periodically to verify that it is within acceptable limits. If the resistance is too high, additional grounding electrodes may be required. It's important to remember that the grounding system is only as good as its weakest link. Therefore, it is essential to pay attention to every detail, from the sizing of the grounding conductors to the installation of the grounding electrodes. By following the NEC requirements and adhering to best practices, you can create a safe and reliable electrical system that protects people and property from the hazards of electrical shock and fire. In addition to the equipment grounding conductor, there's also the concept of the supply-side bonding jumper. The supply-side bonding jumper ensures that the grounded conductor, typically the neutral, is connected to the equipment grounding system at the service equipment or the source of a separately derived system. This bond is critical for establishing a low impedance path for fault current to return to the source, allowing the overcurrent protection device to trip quickly and clear the fault. The size of the supply-side bonding jumper is determined by the size of the service entrance conductors or the derived phase conductors, as specified in NEC Table 250.102 colon. The jumper must be large enough to safely carry the available fault current. The connection of the supply-side bonding jumper must be made in accordance with NEC requirements. It should be connected to the grounded conductor and the equipment grounding system using listed connectors or other approved methods. The connection must be secure and corrosion resistant to ensure a reliable electrical connection. In addition to the supply-side bonding jumper, there's also the load-side bonding jumper. The load-side bonding jumper is used to connect the equipment grounding conductor to the metal enclosure of equipment, such as panels and disconnects on the load side of the service equipment or separately derived system. This ensures that the metal enclosure is effectively grounded, minimizing the risk of electric shock if a fault occurs. The size of the load-side bonding jumper is determined by the size of the circuit conductors supplying the equipment, as specified in NEC Table 250.100.